Assalamu alaikum, dear students. In our previous class, we talked about the oxidation of the alkene using per acids to form the epoxides or the oxiranes. Oxiranes or epoxides are those organic class of the organic compounds having three-membered ring and containing the oxygen is one of the member of the three-membered ring. So last lecture was that about. And also we discussed the mechanism and the characteristics of the reactions, and then we studied the different examples. Today in this class we will study the oxidation of the alkenes using osmium tetraoxide to form syndiols. What are syndiols? Syndiols are those compounds having two hydroxyl groups on the adjacent carbons. They are these two hydroxyl groups are vicinal to each other. They are on those carbon atoms which are adjacent to each other. So these compounds are sometimes called 1,2 dihydroxy alkanes. Sometimes we call it as 1,2 dihydroxy alkanes. So these are the diols having those compounds having two hydroxyl groups attached to the vicinal sides. And what is meant by the syndiols? Syndiols mean on the same side. These two hydroxyl groups are on the same side of the single bond, so they are the syndiols. If one of the hydroxyl is on the other side, this idea would be much more clear when we will draw the Fisher projections like this. What is the name of this compound? 1, 2, 3, 4. It has four carbon atoms. So 1,2 butane diol, or you may say 1,2 dihydroxy butane, and two hydroxyl groups are on the right side of this molecule. So two hydroxyl groups are on the same side, so we can say that this is an example of the syndiol. So we have learned that what are the syndiols. Now what is osmium tetroxide? Is a good oxidizing agent that actually oxidizes the alkenes olefinic double bond to into the syndiol. So let's first discuss the structure of this osmium tetraoxide. It has square planar structure. Four oxygen atoms are at the corners of that square plane. Since oxygen is electron negative element, highly electronegative element, so what it do, it actually pulls the electron density towards itself, making osmium little electron deficient. Since there are four oxygen atoms and all four oxygen atoms are pulling the electron density towards themselves, so making osmium a good electrophile. And and alkene, we know in our previous class, this alkene acts as a good nucleophile. This olefinic double bond, it acts as a nucleophile. So when osmium tetraoxide reacts with an alkene, so what is the product? The products the product is syndiol. Since the olefinic double bond has two phases, so we can draw the diol like this, where two hydroxyl groups are on the front side, or you may draw like this. When two hydroxyls are on the rear side, it will be clear from the mechanism that why I have drawn here the two hydroxyl groups on the front side or two hydroxyl group or on the back side. So in this reaction, the things to remember is that osmium tetroxide is used to convert olefinic double bond into diols. Let's look into the mechanism of this reaction. I'm drawing here another example, and then we will see its mechanism. This is cyclohexene. Upon reaction with osmium tetraoxide in the first and then followed by the on the second stage hydrolysis, we get cyclohexene 1,2-diol. Two hydroxy groups are on the front side, or two hydroxy groups in the case of the symmetrical molecule may be on the back side of the ring. So alkene here acts as a nucleophile, and since it's a partial positive osmium, so what happens in the first step, that this attacks over here, this bond comes here and here, so we get a osmate ester. So we get an osmate ester in the first step. I repeat here that olefinic double bond, it acts as a nucleophile. It has a pi electron density, so that can be donated. This oxygen is electron deficient. Why? Because osmium is electron deficient, it is pulling the electron density towards itself. So what happens, that this nucleophile attacks on here, then there to balance the valency, this bond moves over here, and then this bond moves over here, so we get a cyclic transition state, or this cyclic transition state is called an osmate ester. What happens in the next step is the hydrolysis. This actually the formation of the transition state, and that is transition cyclic, in the cyclic form, is very important. I have to draw here, wait. So the first step is the formation of the osmate ester, and the cyclic transition state is obtained. We know that there are two phases of the pi bond. This nucleophilic attack, it can occur from the upper side of the pi bond. So in this way we will get this diol attack from the upper phase of the double bond. or we may have another cyclic transition state where the attack might have occurred from the lower phase. So I should draw another transition state like this. So we might have the two transition states. The next step is the hydrolysis. What happens when we add water? It attacks over here, this bond moves over here, and this we get negative charge over here. In the next, this proton shift occurs. This when this bond moves over the oxygen to stabilize the charge, positive charge, then hydrogen gets the positive charge, and this oxide ion is a negatively charged. So what happens, this proton shift occurred in the first phase. Again, there would be an attack of the hydroxyl group over here, then there will be the shift of the bond. We will get the oxygen, negatively charged oxygen atom, and then there will be a proton shift. So finally we will get this diol. I repeat here, in the case where osmate ester was formed from the lower phase of the double bond, so you may have the better idea what is happening. This is osmium osmate ester. This transition state is formed when nucleophile attack of the olefinic double bond was from the lower phase. Then in the next step there is the attack of the water or the solvent. When this attacks over the osmium, because it's a partially positive charge, this bond moves over here, and then there is a shift of the proton from here to this negatively charged oxygen. We get this sorry, dotted in the dotted line. We should mention here in a dot. Here again there is the attack of the second molecule of the water. We will get this and then there will be the shift of this proton to this oxide. we will get finally we will get this diol, and here two hydroxyl groups are on the back side of the ring. So what is this? Cyclohexane 1,2-diol. Sorry. The important thing to remember is in this mechanism is that in this mechanism there are two steps. In the first step, there is the attack of the nucleophile, like olefinic double bond here is acting as a nucleophile. First attack of this nucleophile over this oxygen, they getting electron deficient because of this cyclic structure. In the first step, we get this cyclic transition state, that is the cyclic osmate ester is formed. In the next step, the hydrolysis of this osmate ester finally produces this syn 1,2-diols. Again, the first step is a concerted. There is no bond formation and no bond breaking is occurring. Only a cyclic transition state is forming, and this osmium tetraoxide can attack from the upper phase of the double bond or from the lower phase of the double bond. So if it attacks from the upper phase, then we get diols where the two hydroxyl groups are on the upward phase, and if osmium tetroxide attacks from the lower phase, then we will get a transition state like this, and finally upon hydrolysis we will get these diols where the two hydroxyl groups are on the rear side of this ring. Okay, let's go and study few specific examples of this syn hydroxylation, syn dihydroxylation. We will call it syn dihydroxylation because the two hydroxy groups are now attached. This reaction, what are the characteristics of this reaction? Now we are going to study the characteristics of the syn dihydroxylation using osmium tetroxide. The first characteristic was the formation of osmate ester. We get a cyclic transition state. Another thing, this is a regioselective reaction. Let's study what is regioselectivity. In our previous class, I talked a little bit about the regioselectivity, that in a starting molecule, if you have two identical reactive sites, and which site will be the more reactive and which one will be the less reactive, it depends upon the nucleophilicity of the double bond. We will get the two products. One product will be in the major amount, another one will be in the minor amount. So upon what factors it depends that which product will predominate? It depends upon the nucleophilicity of that double bond. So let's study an example where regioselectivity is occurring. This is a starting compound when we react it first with osmium tetroxide in the first stage, and in the second stage we do the hydrolysis, what will be the product? Here you can see that there are two double bonds. Which double bond will react? We know that we will get the syn dihydroxylation. We will get diols, and those hydroxy group will be on the same side. Whether this olefinic double bond will react, or this double bond or this olefinic bond will react, think over it. This olefinic double bond is electron deficient because this group, ethyl carboxylate group, this actually is pulling the electron density itself. So olefinic double bond is no over here because its pi electron density can be delocalized over this electron withdrawing group, making it electron deficient olefinic double bond. But here this double bond is attached to two alkyl groups, and those two alkyl groups are having positive inductive effect, making it more nucleophilic. So syn hydroxylation would occur here. So final product would be, we will get the two products. I am just writing two hydroxyl groups. I'm not working on the stereochemistry. It may be those hydroxyl group may be on the front side, or they may also be on the rear side. We will also get another constitutional isomers, but this product will be major and this will be minor. So this is the regioselectivity of this reaction. Remember, more substituted alkene having more electron donating groups, that is more reactive. So among these two double bonds, this olefinic double bond seems to be the more nucleophilic, so it will attack, and the hydroxylation will occur on this double olefinic double bond. So what is regioselectivity? Regioselectivity is that, so in your starting molecule, if there are two identical reactive sites, so which will react faster, and we will get two constitutional isomers, and one of them is in the major amount. So what is happening over here? This isomer will be in the predominant amount. Another characteristic of this reaction is the stereoselectivity, and that is very important for your examination point of view. We study another characteristic of this reaction, and that is stereoselectivity. Stereoselective reaction. So this dihydroxylation reaction, a syn dihydroxylation reaction using osmium tetroxide with alkene, is a stereoselective reaction. Remember, I hope you would have gone through what is stereoselectivity in previous class. I told you that if in a reaction two stereoisomers are formed from the same molecule because of the presence of already present a functional group, so those reactions are called stereoselective reaction. Here I'm writing an example to make it more clear for you. This is 2-cyclohexenol, or you can say cyclohexene 2-ol. This carbon is an asymmetric carbon. By the way, what is the configuration of this asymmetric center? Is it R or S? I hope you would have gone through that. This is 1. If you will assign the priority, 1, 2, 3. So it's like clockwise. So it's R, R cyclohexene 2-ol. Upon reaction with osmium tetraoxide in the first stage, and then upon hydrolysis, what will be the product? We are getting two products. In the first product, two hydroxyl groups are on the upper phase or on the front side of this olefinic double bond. And in the second product, these two hydroxyl groups are on the rear side of this double bond, or you can say opposite to this hydroxyl group. So we are going to have the two stereoisomers. Which one is in the major amount? Actually, the concentration of two stereoisomers depends upon the already present polar functional groups. I hope you would have understood in our previous class that when I talked about that, okay, the presence of the polar functional sites already attached to the molecule will decide the attack of the electrophile, whether it will attack from the upper phase or from the lower phase. So when there is a small polar molecule like hydroxy or the amino, then the attack of the electrophile will be such that will stabilize these two. So to understand the to understand the reason, let's first draw its transition state. If the attack of the osmium tetroxide is from the upper phase, then transition state will be like this on the same side of the hydroxyl group. We may have the second transition state, so which transition state do you think is more stable? Here in this transition state, this hydroxyl and this oxygen are on the same side of the cyclohexane ring. So there are the great chances of the hydrogen bonding between these two oxygen atoms, and hydrogen is bridging between two electron negative elements. So there are great chances of this hydrogen bonding, which is making this transition state more stable. So this reaction will forward towards that oxidation state which is more stabilized. But here these two this hydroxyl group and this oxygen are far apart on the opposite side of the spring. So this is not a stabilized transition state. So this transition state will be formed, and upon the hydrolysis, two molecule of the water, we will get this final product. So dihydroxylation will occur. Dihydroxylation will occur from the front side, from the upper face of the double bond. So this would be the major product. What is it? Is it stereo selectivity or regioselectivity? This is stereo selectivity. The stereochemistry of the product depends upon the stereochemistry of the already present functional group. We will, in the stereoselective reaction, we get two stereoisomers. One is in major amount and one is minor amount. The amount of the stereoisomer depends upon the stereochemistry of the already present functional group. So thank you so much, dear students. In this class we learned what is the final product using the osmium tetroxide. We learned about the dihydroxylation of the double bond using osmium tetroxide. We learned the mechanism of this reaction. We learned the regioselectivity of this reaction, and then stereoselectivity of this. This lecture is not yet completed. We will have further examples to understand the further characteristics of this dihydroxylation. So thank you so much. Uh, when I will complete this reaction, then I will leave some examples for you to solve, and then in the live class then we will discuss it. Thank you so much.